So at each subproblem, you have a choice to move to the cell right or down. That's your subproblem. And when you write a proof, now proofs for DP can be a little tricky, and I didn't include them here. I would say focus on your recursive formulation and then think about the proof. Because the recursive formulation is easy to translate into a proof or pseudo. Right? So your subproblem here, you'll always state that. You're going to move to the cell to the right or down at each and every single step. And then you're going to identify the pattern of the problem. What type of problem was this? Optimization, because it said give us the maximum number of plants that can be watered. So you'll use the maximum function. And now, does anyone want to probably guess what that formula would look like? Don't worry what's on the left. The left is just like MC of ij equals, what would the function be? If we have an optimization problem that wants us to find the maximum number of crops watered. Okay, max, yes, exactly. So you have a max function, and it takes two arguments, right? And the answer right here was correct. You take on one, so one argument will be going, where can Gary move? Right? And then the other argument would be down. So for this problem, MC of ij equals him going to the right or him going down. Plus, okay, now here's the other thing. For this problem, we're going to take the garden of that current step. Because remember, it's about overlapping subproblems and storing them into our cache. We're going to store what the current tile that we're on is plus where we're moving to, right? Because we're counting each tile that we're stepping on, right? And then time complexity is m times n, because it's an m times n board. Okay, top down. Again, the easy thing is straightforward. Once you have a recursive formulation, it's like the key to the whole problem. Remember, top down is recursive, bottom up is iterative, right? So we're going to go and we're going to say, okay, if I, is that, okay, this should be I, not 1. Someone was colorblind that night. Sorry. It should be I greater than m or j greater than n. Then we're going to return infinity. Infinity, if you remember Dijkstra's, you know, infinity is like, okay, I can't go there. It's like too big, right? It's not, so it's like returning that, okay, this, we're not going there, right? So if I and j, that tile is not in the cache, then oh my god, what do we have here? We have what we have up there. Well, cache of ij equals the maximum between going right or going down, and then we added that tile that we're at, because it's like we're adding on top, right? Any questions about the top down? Yeah, it's Yusuf.
I don't really get what garden ij is.
It's like the current tile that you're on, inside of the cache.
Okay, so is that keeping track of?
It's keeping track of the maximum number of tiles that you're, so, remember how it's like overlapping?
The amount of crops that we're able to take
because, yeah.
Like it's either 0 or a number, or 1 or something? Or
Yes, actually, yeah, because this would be 1. So I put plants to make it visual, but those would be 1.
Okay.
So that's a great question. I was not thinking about that when I designed that. But it's like 0 is okay, there's nothing there, we didn't water. But the plants are 1, so we watered something there. But
so each turn we keep track of if we're on a tile we watered or not.
Exactly. Any other questions? Cool. Let's quickly move. Bottom up, same thing. You took the recursive formulation that you have, but now it's iterative. Now, this first line is a little Pythonic, but what I'm writing here with the infinities, which you also see up here, is that it's zeroing out the table. That's the concept. So iterative is different. So the bottom up is different from the top down in this way of imagine that you're moving on a board where you just don't know what's next to you. So I probably should have had this as a 0 by accident up here. I'll fix that on the slides when you get them. But think of it as, so I use 2 different analogies depending on 2 different audiences in my office hours. I don't want to be gamer-centric, but if you're a gamer and you ever played a game with a fog of war, I like to describe it that way. Or if you're not a gamer, think that you're stranded on an island and you have a map and you're blotting it out. You can only see, I don't know, one tile of distance, right? So then as you move, you discover more tiles. That's what a bottom up is. On a table representation. So a negative infinity is a tile that you can't see. Except on here for this top tile, Gary can see that. I just need to change it to a 0. But Gary can see here and here, because why? Gary can only move right or down, right? But Gary already knows where this tile is, that's far, right? So that's what you're doing here. You're starting with a table that you set to 0. All those zeros or infinities are tiles that you can't see. But Gary knows how to move right, Gary knows how to move down. They can navigate through the table. Only left, like, right or down. Now, you have an outer for loop going from, iterating for that I, and then you have an inner for loop iterating for that J. Different from the recursive way, but you still notice you have the same termination condition of 1 to m and 1 to n. Same thing as with recursive. And then this is why I kind of lean towards memorization, because it looks like someone just barfed out some code, right? So then you have okay, if the current tile down is infinity, or sorry, if the current tile to the right is infinity, or the current tile down is infinity, then move to it and do that, and then you have the recursive formulation down here. I said the memoization way, which is recursive, is more expressive, because it's recursive, and you don't have to write out all this extra noise. But do you see the difference, and can you understand and identify how each slide, each pseudocode comes from the recursive formulation? Question?
Will they ever ask you on an exam on a DP problem to give both the bottom up and the top down solution?
No. Or Caitlin question, or call it question. Caitlin, we never asked them to give both bottom up or top down in Wu's class, right? Yeah, Khaled did do that on the exam. In Wu's class, you don't. I'll confidently say that because Caitlin said that.
But might you be given a solution to a DP problem and asked to differentiate if it's top down and bottom up, what kind of problem?
Not on my exam. If that was your exam, that's cute. But not on mine. No, it's more like they'll give you the same sort of problem. They'll ask you explicitly to give a DP solution, and it's a matter of subjective taste, whether you like it bottom up or top down. Yep.
You say it's subjective, but if I wanted to find something that was looking to use, just mention the space complexity.
Yeah.
The stack, so is that why you prefer bottom up?
No, I prefer top down. Sorry. I prefer, okay. Again, it's a matter of taste on whether or not you like recursion in general. If you like recursion, you'll probably click the memoization. It's like that debate. It's like, oh, well, recursion, it's expressive. Oh, well, recursion uses the, it fills up the stack overflow. And there's, debating to each other in the dark and no one cares.
So if my concern is not how understandable or my algorithm is, then I would probably choose bottom up.
Yep, exactly. And then you'll probably end up debating Khaled because he likes top down. So it's a matter of taste. So if you like bottom up, go with it. I will warn you one thing. A lot of solutions online tend to be bottom up. If I watch a lot of neat code videos, it'll be bottom up. If I go to I don't know, Geeks for Geeks, God forbid, it'll be bottom up, and then etc. But yeah, it's up to you, and whichever one will score your points in the exams gets cited. But.
So just to clarify, number 1 is subproblems.
Uh-huh.
So that's going right down.
Yep.
2 is identifying the patterns, and is knowing that you have to do optimization and that you will need to use max. And then the third one, which is being operable, is basically the whole
yeah.
and so.
Yeah, so the third step is making your recursive formulation, which is piecing together the former 2 points. So which sounds like you got it, so hopefully this will be good. So now I pass it to Santiago with longest common subsequence. Have fun.
I dreaded this moment when they said they were going to post it to review. But yes, longest common subsequence. We have it's another DP question. So first thing we're going to do is we're going to take a look at what problem assessment is, right? So given 2 strings, return the length of their longest common subsequence. And if no such common subsequence exists, then we're just simply going to return 0. So First, we're going to ask ourselves, what do they mean by common subsequence? Well, we know that a subsequence, it's a derivative of an original string without manipulating the order of the elements. Okay, so it will have the same order of elements, but it will be a new type of string, right? Whether we delete an element or change it. Now, a common subsequence will be that, but with similar elements between two or more strings. Okay, so process that information because that's what we're going to solve. So we have some examples right here. String 1 is a string of DNA sequence. String 2 is as well. And we're going to try to see if we can find the longest common subsequence. So let's tackle this. So first, we're going to state this, our subproblems. So what do you think is our subproblems here? And remember, we're trying to find the length of the longest common subsequence. So does anybody want to tackle this? What do you think the subproblems will be? Yeah, any guesses? Yep.
All subsequences of each string.
All subsequences of each string. Okay. Do you have any other guesses? I guess we're going to move on. Yeah, we're going to show it. We're going to show it. All right, so we're going to identify these subproblems. So first, we need to imagine ourselves what the length of each string is, from string 1 and string 2. We can't assume that they will share the same length, right? We can assume that string 1 will have a length of n, and that string 2 will have a length of m. N and m could be the same, but they could also be different, which is why we're expressing them with different variables. Now, the amount of subproblems that we have will be m plus 1 times n plus 1, right? So we're going to explain where the plus 1 came from early on once we talk about the recursive formulation. So now that we have identified our subproblems, we're going to look at step number 2, which is we're going to find the pattern, right? So identifying the pattern. So this is an optimization problem. So what are we looking for? We said we're looking for the longest, the length of the longest common subsequence. So what function do you guys think we're going to use? I heard max? Okay, max. That's correct. We're going to use max. All right, and now we're on to our third step, which is our recursive formulation, our formula. So the way I like to create my formulas when it comes to DP is to think about the scenarios we're going to face. So remember, we're looking for the common subsequence. What does the word common, mean to you? We're looking at two strings, and we're trying to find the common elements. So what are we most likely going to do? Compare them, exactly. So we're going to compare them. So that means that we have at least two scenarios. What are these two scenarios? There we go, that they are equal or not, exactly. So what are we going to do if they are equal? All right, let's tackle that scenario. What are we going to do if in a position, in our current position, we find an element in both strings? What are we going to do there? Any guesses? There you go. We'll add it, right? Because we're looking at the length, right? Exactly. So, correct. We're going to add it. And then after we add it, we're going to go down the string, right? We're going to down both strings. So what about the scenario in which they are not equal? And it's kind of spoilers over here, but what does this formula mean here? Try to, what's your interpretation of this formula?
Does it look like one you already saw?
Mm-hmm.
Regarding the
Yeah. Somebody said something? Yeah.
similar to the garden problem.
Yep.
It's just like the garden problem, so then, I'm just kidding.
Oh, no, you're good, you're good. Yeah, it is similar like the garden problem. Remember, we're moving left and right. Not left. Bottom, right, yeah. All right, sorry about that. But remember, we're only moving one direction, right? Which is, we're moving down the string, right? To the left. And we're only doing that in two scenarios, whether the elements are the same in both strings or not. So when we have the same elements, we move both down the string, right? Because there's no reason for us to stay in that position because we already found a common element. But what about if we haven't? That's why we're going to use the max, because the max will help us optimize, right? It's going to help us to decide whether or not which position we stay on. So if the max is in I, then we're going to move down J. Or if the max is at J, then we're going to move down I. And then we're going to do that, so on and so forth, until we run out of the length of the string. Okay, so we're going to now look at top-down, memoization. So here, as you can see, we have not talked about the base case yet. So base case. Can anybody tell me what the base case is? Exactly. Yeah. Those strings. Yeah, because remember, if no common subsequence exists, then we have to return 0. That's what the problem stated, right? So that's why at the beginning, if you remember, we have m plus 1 times n plus 1. Because if you try to visualize the cache, it's going to be an m plus 1 rows and n plus 1 columns, right? I did that visualization wrong, but yeah. Oh yeah.
So that visualization thing that Santiago's explaining, it's on Wikipedia. There's some footnotes on the slides before. You can see it there. And there's also Abdul-Bari video that explains it. So if the visualization doesn't come to mind right now, don't worry, it can come to mind later when you study and look at more problems like this. So I'll hand it back to Santiago.
Thank you. Yeah. All right. So back to the table. That's why we're stating over here when we're building our cache that 0 through n and 0 through n, because we want the first column to be 0, and we want the first row to be a row of zeros, because that's what we're going to be comparing it to. When we get down the length of the string, we're going to meet that 0, and that's where we're going to stop, because we finally come at our end. So yeah, you guys can check out the Wikipedia and sources, of course. So now that we have defined our cache, we're going to look at the actual memoization, which is the inner function right here. It's going to have the length of the first string, which is I, and the length of the second string, which is J. So of course, our base case would be if I is 0 or if J is 0, we return 0 because no such common subsequence will exist. Now, if we have not calculated that subproblem, that's what we're going to do right now. That's what the statement basically means, right? Because that's DP. We want to calculate it only once, because we don't like wasting time. So yeah. So here's our first scenario. If both elements are in the string, then we're going to add 1, because that's our length, right? And then we're going to move down the string, both strings. And of course, add it to the cache as well. Now, second scenario. What if they're not in the string? What if they're not equal? So if they're not equal, then let's take the max, right? We're going to optimize our way. Let's try to figure out in which position we should stay and in which position we need to move down. And then after that, everything else should be calculated. So if we go down the string and we already calculated at that position, then we can simply just return hash of ij. Then after that, our answer will be this. So you can clearly see that the time complexity of this is O m of n, right? The formula to find time complexity for DP problems will be the number of subproblems times the amount of time it takes to solve each one. Now, it's not m of n, it's actually like m times n plus 2mn plus 1. But we're not gonna get into the specifics of that. So yeah, wait, just simplify to MN. That's good enough right there. Yeah. All right.
Anyone freaked out by the inner function, by the way? Are you guys okay with like defining a function inside of a function? That's very like Pythonic. I know a lot of people would do like C++. You don't get it? Okay, gotcha. So it's like, how do I explain this? It's like you have a function, LCS. You're gonna call that in main, right? Now you can't do this in C++. You can do it in Python. But this outer function, you pass in the parameters to it. But this, I'm gonna sound like a nerd, I'm gonna mention like OOP. This inner function here is encapsulated, which if you remember from 1437, it just means it's like private to this space, right? It's hidden away. So when you call LCS, you don't care that there's some LCS helper function being called, you just want LCS to give you what you want. So this is just a function that is neatly tucked away inside this other function. So what you're doing is you're passing in string 1, string 2, and then this function LCS, which is the outer function, is doing the magic of, okay, I have this algorithm that I gotta do, so let me just call my friend here who happens to live in my house. It's a roommate. Think of it like that. Is that good for everyone? Cool. Back to Santiago.
All right. Now that we look at top-down, we're gonna look at bottom-up, the iterative way. All right. Bottom up. So notice how it's iterative, right? Well, yeah, we got our for loops. So first off, we're going to start off by, initializing our cache, same way as we did, from 0 through m, and then from 0 to n, right? Define it. Then from there, since we already said that our time complexity is mn, we're going to have two for loops, like nested, right? First off, from I to m, we're going to look at the rows, or at the columns, and then from 1 to n, look at the rows. So similar, right? Look at our first scenario. What if we encounter two elements in the same string? Well, we're going to do the same thing. First off, we're going to move down the string because we don't need to be there. We already found what we're looking for. And then we're going to add 1 because that's the length of the longest common subsequence. Then, in our second scenario, what if they're not the same? Then we're going to look for the max, because that will help us optimize our way of finding the longest common subsequence. We need to figure out which one should we stay at. Should we stay at I or should we stay at J? Once we find the max, it will tell us where we need to stay and which string we need to go down. Then after that, after we keep looping, we should come to our answer, which will be located over here, hash m of n. We simply return it, and everything is smooth sailing. So yeah, time complexity is the same. Don't even worry about it, So any questions about bottom up? Right? Pretty similar to Gary the Gardener. Definitely not another.
Okay, so now that was it. We're over 7. Probably like 10 minutes over. But I have bonus questions in the slides. These will be handed to you, and it will help you study. So if you need some problems to practice, here they are. First one, I gave some random recurrences. Yeah. So those should be straightforward. Just practice those. Then this is a key point I'll give. So we looked at LCS with a dynamic programming solution. You can give a backtracking solution. Backtracking is typically worse than dynamic programming. So on Woo's exam, when I took it, a question will be worded where it would be like, give us a dynamic programming solution. But if you couldn't give a dynamic programming solution, you could give a backtracking solution, and it'll be like minus 25 points or something. You'd bleed a little from it, but it's better than getting 0 like I did. So good to practice backtracking and comparing it with a dynamic programming solution. And then here's another dynamic programming question, map sum. It's typically used to teach dynamic programming. You can ask us about this one. We have the solution. So if you go to our Discord and you try this one out, we can kind of converse, talk, go back and forth about that. And here's one more. Another dynamic programming problem is minimum palindrome. So again, optimizing, but this time it's minimum, so you're probably not going to use max. You're going to use the min function. These slides will be available to you if you're in our Discord. And yeah, just good luck. So thank you for joining. Thank you for staying after what, like 7:15 or something. We went over time. So yeah, thank you and good luck on your exams. You can ask me or the others, or probably just me. I don't want to keep them here hostage. So yeah, you can ask us any questions you like. But thank you.